Chapter 12, Section 12.1, we're going to describe equilibrium of phase changes. We're going to write equations to represent phase changes as endothermic and exothermic, and we're going to define equilibrium. So first we're going to name all the different phase changes that there are. First phase change will be freezing. The opposite of freezing is going to be melting. Then we have vaporization. Opposite of that is condensation. Then we have sublimation. And opposite of that is deposition or deposition. It's important to note that there are two different types of vaporization. There's boiling, which is vaporization when heat is applied, and there's evaporation, and that's vaporization at a given temperature. So no heat necessarily needs to be applied. Okay, now let's talk about what these phase changes represent. Freezing is going to be when changing from a liquid to a solid. Melting is from a solid to a liquid. Vaporization is from a liquid to a gas. Condensation is going to be from a gas down to a liquid. Sublimation is going to be from a solid to a gas. And deposition is going to be from a gas to a solid. So endothermic means energy has to be absorbed. And exothermic means energy needs to be released in the change. So freezing, because a solid has less energy than a liquid has to release its energy to become a solid. So freezing is an exothermic process. Melting, a solid needs to absorb heat in order to become a liquid, because we heat ice, we want it to melt. So this is going to be an endothermic process. Vaporization, you have to heat a liquid to change it into a gas, and so that makes it endothermic. Condensation, a gas has to release its energy to become a liquid, and so that's exothermic. Sublimation, a solid would have to gain energy to become a gas, so it has to absorb energy, so that's endothermic. And from a gas down to a solid, that would be the opposite, which is exothermic. A gas has to release energy in order to go down to being a solid. Now, the most important part of this entire chart is writing the equation. So for freezing, we're going to write that a liquid is going to release energy. So a liquid releases energy to become a solid. In melting, a solid has to absorb the energy to become a liquid. So notice we have our reactants and our products. On the left side of the arrow, our reactant here is liquid. On the right side of the arrow are our products, which is energy plus a solid. And if you find energy on the reactant side, then on the product side, then it's going to be exothermic. Whereas if it's endothermic, your energy is on the reactant side. So for vaporization, a liquid has to absorb energy to become a gas. And for condensation, a gas has to release energy in order to become a liquid. For sublimation, a solid has to absorb energy to become a gas. And for deposition, a gas would have to release energy to become a solid. So here's a diagram to kind of help represent all these different phase changes. And you'll notice that here are the equations again. And anytime you have energy on the left-hand side, then this is an endothermic process. And when you see energy on the right side, it's an exothermic process. Endo, you have to absorb energy. Exo means release of energy. I like to think of exothermic as the energy is exiting. So you're going to always find it on the right side or in your products. And then here is showing you the two different phases paired off, or the different phases are paired off. And that's because these phases can exist in equilibrium with one another. So melting and freezing are occurring simultaneously depending on whether or not it's being heated or being cooled. Condensation and evaporation can happen simultaneously depending on if it's being heated or being cooled. So equilibrium is going to be two opposing or opposite processes that occur at the same time at the same rate. For example, when freezing and melting occur, the phase change is considered to be in equilibrium. So the definition of equilibrium, it's a very stable reaction. It's a constant phase changing between products and reactants, where you have the forward and the reverse reactions occurring equally and simultaneously. There's no net change in concentration. The system is dynamic between the two opposite reactions or system. So, in short, chemical equilibrium is a state of dynamic balance in which the rates of forward and reverse reactions are equal and there is no net change in concentrations. What that means is I could have a certain concentration of A and B, and I can have a certain concentration of C and D. So let's say we have a pile of rocks for A and it's that high, and I have a pile of rocks for C and D and it's that high, and I have an ant traveling one rock at a time this to the right, and I have a second ant carrying one rock at a time to the left. So here I have one rock moving from left to right, and I have one rock moving from right to left. So at no time will the piles get any larger or smaller than they currently are. So there's no net change in their concentrations, even though I have a forward reaction occurring at the same time as a reverse reaction. But they are happening at the same rate equally, so this is why there's no net change in my concentrations of reactants and products. There's a really great demonstration visually that you can see, and it's on the YouTube channel. Also, it's called Bailing Beakers, Equilibrium in Chemistry class. So give it a try, watch it, and apply the definition that you see here to the demonstration shown in the video.